I feel like our class has rounded a corner, which is kind of exciting. I feel like the students who want to be successful have accepted, they've gone through their stages of grief, anger, bargaining, denial, sadness, acceptance, depression, acceptance. And we've come to acceptance. And we just know that this class is going to be work. And it really is just work. Okay, so chemical equations, this is chemistry. Chemical equations talk about reactants being converted into products. And there's two ways of classifying typically. And so the first way of classifying is by these 5 types, which I'm going to go through today. And then the other way of classifying is redox or not, which I'll touch on today, but really that's next week's stuff. Okay, so a chemical reaction can be one of these 5 types. And the first one is synthesis. And synthesis is simply we have something small, 2 small things that combine to make something larger. It doesn't have to be 2 things make one. It just has to be, I start with several things and they combine to synthesize or to make something new. Decomposition is the opposite of synthesis. It's where something large breaks apart into smaller pieces. A lot of times that involves, but not always, that involves heat. Combustion is what it sounds like. Let's light something on fire. So for combustion, it's fuel plus oxygen react to form carbon dioxide and water. For the subscript for water, I'm using gas. Why? Well, when you light things on fire, it gets hot. And so the water produced is water vapor at first. What is the fuel? The fuel could be anything that has carbons and hydrogens, or maybe carbons, hydrogens, and oxygens. In our class, the oxygen is always in excess. Is that true in real life? No. In real life, when we combust things, sometimes we don't have enough oxygen, and so we don't get carbon dioxide, we get carbon monoxide. There weren't enough oxygens to give that carbon 2 oxygens for each carbon. And then sometimes there's not enough oxygen, and so we just make soot. And so if I have amorphous carbon, amorphous is just a fancy word that means without shape. If I have amorphous carbon, it's called soot. But in our class, we're always going to have enough oxygen, and fuel is always going to be the limiting reactant. So our products of combustion will always have enough oxygen. We'll get CO2 and H2O. Single displacement and double displacement reactions are really important in our class because these reactions occur in water. And a lot of general chemistry is looking at the chemistry that happens in water. For single displacement, we're going to start with an element and a compound that are going to react to form a different element and a different compound. For double displacement, we start with 2 compounds. And the cation of the first combines with the anion of the second. And the cation of the second combines with the anion of the first, cations before anions. And so it's kind of like 2 couples go to a dance and they switch partners. And then if the partners stick, if the products happen, we have either formed water or a solid or both. So for for double displacement, there are 2 flavors of products. We could have precipitation, which is a fancy word that just means a solid was formed. What does that solid look like? It could just look like, oh, it was clear, but now it's cloudy. Or other times it looks like, oh, I see something just came together and formed. I see a solid in there. So sometimes a precipitation, which is an insoluble solid, is a little bit subtle. You're going to witness that this week in lab when you do an experiment with some droppers that are full of solutions. You mix them in a spot plate and you're looking to see, did any solid form? Those are precipitation reactions. And then the other flavor is called a neutralization. And a neutralization is just an acid-base reaction that forms water. So acid plus base makes water plus salt. What is a salt? It's just an ionic compound. It's an ionic compound that isn't a base. It isn't a hydroxide. Okay, so those are the 5 general reaction types. Why would we want to classify things besides to answer a question on a test like what type of reaction is this? Why would we want to classify things is because once we classify it, it really helps us balance that equation. There's a strategy to how you put the coefficients to balance an equation based on what kind of equation it is. So I want to talk about redox. Redox is a contraction, sort of. This has to do with reduction, oxidation reactions. So when I say reduction and oxidation, does anything come to mind? Here's a sentence that I've said in our class. Metals oxidize easily. Metals are easily oxidized. What does that mean? Well, here's iron, and I might have a bike that has a frame that is steel, and steel is mostly iron. I don't want to leave my bike out in the rain because over time, iron is going to react with the oxygen in the air to form rust. When iron starts to look sort of that rusty dark orange color, it's because it's oxidized. Iron went from being iron that is neutral, 26 protons, 26 electrons, some neutrons, to iron that has a +3 charge. How did it do that? It lost 3 electrons. Lose electrons is to oxidize. Where did those electrons go? They went to the oxygen. So oxygen gained electrons to form oxide. Oxygen can gain electrons and be reduced. Gain electrons, reduced. What does reduced mean here? It means it went down in charge. Oxygen did have a charge of 0. It was neutral as an element, but now it has a charge of -2 because there's more electrons than protons. And so a lot of times when we talk about redox, we draw a number line. And if something is oxidized, the charge has gone up. But oxidation can't occur without reduction. The charge has gone down. However many electrons were lost, the same number of electrons have to be gained. And so right now I have 3 and 4. Those aren't the same number. When we do redox reactions, we'll say, oh, well, I need that to be the same number. So let me say this happened 4 times. And this happened 3 times. So 12 electrons are lost and 12 electrons are gained. So that's a topic for next week. And the idea is in the process of this, as this chemical process occurred, where electrons transferred, that's redox. So here we have, but today we're focusing on balancing equations. So let me go back to that. I have 3 oxygens here and 2 oxygens there. And those are different numbers, odd and even. So I need to shoot for the lowest common multiple. I'm going to shoot for 6. So maybe if 3 oxygens were reduced, 2 iron 3 oxides would be produced. And now I notice that I have 2 chunks and there's 2 irons in each chunk. So I must need 4 irons here. So To balance a redox reaction requires extra steps, but this one I could do by inspection, which is how we're going to do it in class today. We're just going to look and say, do I have the same number of things on the left and the right? And we're going to make something called a T-table where we look at reactants and products. And then we'll consider atom by atom, even though some of the atoms are ions and some of the atoms are sharing electrons in a covalent way. And I'll start counting. I have 4 ions on the left, and I have 2 times 2, 4 ions on the right. I have 6 oxygens on the left, and I have 2 times 3, 6 oxygens on the right. This is a balanced equation. So I'm mentioning redox. We'll focus on it next week, but I want to come back to this. For the 5 types, are they redox or not? Double displacement are never. Single displacement are always. Combustion is always redox. There's always electron transfer. But for synthesis and decomposition, it really depends what the reactants and products are. Sometimes it's redox and sometimes it's not. Questions? Okay, so today we're going to focus on the 5 reaction types. Why? Because they're going to help us balance equations. So I'm going to start at the top and talk about if it's a synthesis, do it this way. If it's a combustion, do it that way. Okay, so for synthesis and combination, I'm going to start by using my good nomenclature to correctly write the reactants and products. Magnesium metal, or magnesium, or elemental magnesium, means the atom, the element as it exists. And oxygen gas is O2 because oxygen is a diatomic element. React to form magnesium oxide. Magnesium is a +2 metal, oxide's a -2 nonmetal. They come together in a 1-to-1 ratio. There's my product. So the first step in balancing equations would be to correctly write the reactants and the products. Correctly writing the reactants and products requires nomenclature. It requires things like we remember what the polyatomic and diatomic elements are. Once we have correctly written the nomenclature, we don't touch the subscripts. We simply add coefficients to balance the equation. For a synthesis reaction, where I'm starting with 2 things and ending with 1, I would start with the more complicated thing. For most of these, I'm going to start with the thing that has the most letters and numbers. So I'm going to start with the product side. And if I have a diatomic element, I'm going to start there. So I have 1 oxygen, 2 oxygens on the left and 1 oxygen on the right. I need 2 of these. Once I have balanced the oxygens, I'm going to look at the other element in the compound. There's 2 magnesiums. I put a 2 here. And then I check to see, I think I'm done. Is this a balanced equation? Well, on the reactant side, I have 2 magnesiums and 2 oxygens. On the product side, I have 2 magnesiums and 2 oxygens. Yep, that's balanced. If we were doing a decomposition, which is the opposite idea, something big breaks down to make smaller things, I would start with the reactant because it's more complicated. The first step is always good nomenclature. So potassium chlorate, it's a 1-to-1, decomposes upon heating. I'm going to put an arrow, a triangle, which stands for delta, Greek letter D, which stands for change. I'm going to put that over the arrow to indicate that we have added heat to this. To form potassium chloride and oxygen. Because I'm starting with, it's a decomposition, I'm going to start with the reactant side because it's more complicated. There's more capitals and subscripts. and RXT means reactant. Again, I'm going to focus on the diatomic elements first, and I notice that I have in every chunk, every formula unit, there's 3 oxygens on the left, but these come in packages of 2, so I still need to shoot for 6. I put the 2 as a coefficient in front and a 3 as a coefficient in front. Now, once I've added the 2 in front of potassium chlorate, I'm going to look at the other elements. 2 potassiums on the left, 2 potassiums on the right, 2 chlorides on the left, 2 chlorides on the right. I think it's balanced. Let me make my chart for bookkeeping. And take every element individually. That's balanced. Now, just by reading the textbook, you're probably familiar with subscripts. We've talked about states before. What are the states of matter? Solid, liquid, gas, and then we're going to include aqueous, which means mixed with water. We call it a state, even though it isn't really a state. When we're writing balanced equations in Chem 3A, and even Chem 3B and 1B, we don't necessarily know the states. At some point, you will start to be comfortable with states, but I'm never going to test you on states in Gen Chem because we're still learning. But I want to say some things to you that you already know. One is, you know that magnesium is a solid at room temperature and pressure. How do you know that? Because you have a periodic table that you got at the beginning of the semester, I believe. I think you've seen it, that is colored with solid is in black, the symbol is in black, gas would be in red, and liquid would be in blue. And there are only 2 elements that were blue at room temperature and pressure, and those were bromine and mercury. So you have some familiarity with metals. You know that metals typically are solid at room temperature and pressure. You're familiar with oxygen, it's a gas. Now this here is an ionic compound, and I want to tell you something about ionic compounds. The only 2 states that are possible at room temperature and pressure are solid or aqueous. Water is sometimes able to pull ions apart. So if this is in water and it's soluble, I would write AQ. But probably it's solid. There's nothing to indicate water here. So if you take a guess and you write the states, because you're trying to put pieces together in your mind, things that you know, and it does make sense to have states in balanced chemical equations, great. And if you don't, or if you do and you do it wrong, it's okay. Okay, so here I have an ionic compound, potassium chlorate. If this isn't in water, and it probably isn't because we're heating it, that would be a solid. Ionic species are solid or aqueous. And then I know oxygen is a gas. So for the first 2 classifications, just start with whatever the bigger thing is. Combustions are balanced differently. So here we have butane combusts, and I would have to tell you what the formula for butane is. For combustions, you'll be given a fuel, and then you have to know to add a reactant and what the 2 products are. You won't be told, you're expected to know. The other reactant is oxygen, and the products in our class are always complete combustion products. Enough oxygen, carbon dioxide, and water. For combustions, always start with the fuel, and do carbon and then hydrogen. And then once you figured out carbon and hydrogen, the last coefficient goes in front of the oxygen. So let me start with the fuel. There are 4 carbons on the left. I need 4 carbons on the right. There are 10 hydrogens on the left. I need 10 hydrogens on the right. Because each water has 2 hydrogens, that means 5 units of water. And now I'm going to add up my oxygens here and see what I get. I have 4 times 2, so there's 8 oxygens in the carbon dioxide. And 5 times 1, 5 oxygens in the water. So there are 13 oxygens on the right. Problem is, I can't get an odd number out of something that comes in pairs. So what I'm going to do is I'm going to change the coefficients. I'm going to double everything that I already have. I had an implied 1 here. I make it a 2. This 4 becomes an 8. This 5 becomes a 10. And now I have 8 times 2 is 16. 10 times 1 is 10. 26. I have an even number. 13 oxygens. So for balancing combustions, start with the fuel and end with the oxygen. Oh, here's another combustion, propanol. Propanol is C3, let's see, C3H8, but it's H7OH. So go ahead and add oxygen, and then on the product side, put carbon dioxide and water. And when you're balancing oxygens at the end, remember that there is 1 in the fuel. Okay, so here I have even plus 1 is going to be odd, but I have an even number there. So I'm going to have to do that trick where I double everything I've already balanced. What have I already balanced? The fuel. I started by thinking it was 1, and the carbon dioxide and the water. Ethanol, C2H5OH. Ethanol combusts. Okay, so for combustion, you have to remember oxygen is also a reactant, even if the fuel contains oxygen. And our products are carbon dioxide and water. Start with the fuel, do oxygen last. Okay, single displacement is sometimes called single replacement. And this idea is I have an element and a compound, and if the element is a metal, it's going to take the place of the cation. And that's what's happening here. If the element was a nonmetal, it would take the place of the anion. If we were on ground, there's a lab we would do that would involve that. But we're not on ground, so let's just focus on metals for now. Okay, so copper means elemental copper, copper the solid. And elements have an equal number of electrons and protons, and so there's no charge. Silver nitrate, silver as an ion is +1, nitrate is a -1. They come together in a 1-to-1 ratio. And single displacement are always redox, which means electrons are going to be transferred. What's going to happen here is that copper is going to lose 2 electrons to become copper 2. And then silver ion is going to become silver metal. How does it do that? It has to gain an electron. And the number of electrons gained and lost have to be the same, so this has to happen twice. So I really have 2 silver ions gaining 2 electrons to form 2 silver atoms. Electrons lost equal electrons found. So that's what would be happening in the water. And we're trying to keep track of that here. And so at this point in your learning, you might just think, well, copper is going to take that spot. Copper 2 is going to need 2 nitrates. And then silver is going to become the element. In reality, to balance redox reactions, we have to do this process. We'll focus more on that next week. For this week, we're going to do it by inspection, which means I'm just going to look at it and balance the atoms. So for this week, I'm going to have to tell you what the products are because you won't be able to predict products this week, but that'll be coming pretty soon. Okay, so for this, for single displacement and double displacement, it doesn't really matter where you start. You're just starting with something that looks complicated. And to me, this one looks more complicated, so I'm going to start there. I'm going to start with the product that is copper 2 nitrate. I could have started with the other salt, silver nitrate. It doesn't matter. And so I look here and I say 1 copper on the left, 1 copper on the right. Copper's good. 2 nitrates on the left, 1 nitrate on the right. I better add a 2. When I added that 2, I now have 2 silvers. I'm going to need a 2 over here. So I'm just kind of pinging back and forth between reactants and products and trying to get the right number of atoms on each side. And when I do that, when I first balance salts like copper 2 nitrate, I leave the chunks of charge together. Nitrate on the left, nitrate on the right, things like that. But when I'm ready to check and see that I have the right answer and I do my T-table with reactants and products, then I break things down into atoms. Copper, silver, nitrogen, oxygen. This T-table is really just for you to verify that you have balanced things correctly. When you show me your work, I don't need to see that. And you need to use T-tables until you don't need them anymore. So think of them as being kind of like training wheels to make sure you got the right answer. And when you're comfortable without them, you can just do it in your mind. That's totally fine. So at this point, there's somebody out there that's probably going, I don't know how she got 6 oxygens on the product side or something like that. But usually people are reluctant to speak up, especially in this new online environment. So does everybody know why I have a 6 here? 2 times 3? And why I have a 2 here? 1 nitrogen in each unit, but there's 2 units. Okay. So there's 3 flavors of single displacement or single replacement, and I call them displacement. The first flavor is we have a metal replacing a cation. Copper metal became copper 2. Copper metal took silver, which is a cation, silver ion's place. And then the next 2 kinds are hydrogen replacing a cation. And let's see. How to open the molecular formulas of a covalent compound right now. Okay, so the next kind would be, we're going to take a metal and some kind of acid, and the metal is going to replace the hydrogen. So this would be metal replaces hydrogen in acid. So you know that acids react with metals to form hydrogen gas. That's what's going on here. And then the third kind is where the metal replaces the hydrogen in water. And that only happens when the metal is super active. Okay, so here we have elemental zinc, just means zinc. And hydriodic acid. So hydroic acids come from ides. Here's iodide. So let's add an H+, and that makes hydriodic acid. To form zinc iodide, so zinc is a +2 cation, iodide is a -1. We're going to need 2 iodides. And hydrogen gas. Hydrogen is a diatomic element. There we go. So the zinc is becoming the cation for the iodide. The zinc is replacing the hydrogen. For this one, I just want to remember that hydrogen is H2. Where did that the acidic hydrogen is going to become gas, so we must need 2 of those to form the gas. And then I just jump in. I've got 1 zinc, zinc looks good. I've got 2 iodides, iodide looks good. I've got two hydrogens that are acidic. They're going to become hydrogen gas. I think this is balanced. So metals generally react with acids. There's a short list of metals that are not acid reactive. So inert metals are the ones that you can pour acid on and they don't bubble. They tend to be metals that are used for coinage. We would hate our money to disappear, bubble away, if we poured vinegar on it, and jewelry. So silver, gold, copper, platinum, those are inert, but most metals are going to react with acid. Now, there are some metals that are so reactive, they will react with water. Metals that will react with water are alkali metals, and then some alkaline earth metals. Magnesium and calcium will react with water. So there's like basically in our real world 6 metals that'll react with water. When they react with water, they're replacing the hydrogen in water, but they're only replacing the first hydrogen. So when you balance single displacement reactions that involve water, and then pretty soon when we look at double displacement reactions that are neutralizations, I want you to look at water like this. There was a hydrogen that came from an acid and a hydrogen that's part of a hydroxide that came from a base. So instead of writing H2O, I'm going to write it this way, H, 2 H's and an O. So sodium metal is so active, it reacts with water. And I'm writing it for single displacement reactions and in double displacement neutralizations as HOH. When it does that, it is only replacing the first hydrogen. And when it does that, it makes hydrogen gas. So if this hydrogen gas was made from the acidic hydrogen, I'm going to need 2 waters, which means I'm going to have 2 hydroxides, which means I needed 2 sodiums. Questions? Okay. The last kind is double displacement, which is also called double replacement or metathesis, but metathesis is a very old word. I'm going to call it double displacement. And here we're going to have 2 salts change ions, like this cation is going to pair with the other anion, or we're going to have an acid plus base make salt plus water. This first one is 2 salts, and so we're looking at precipitation reactions. Potassium chloride and lead 2 nitrate react to form potassium nitrate and lead 2 chloride. For a double displacement reaction, it doesn't matter where you start. When you're doing single displacement, we're really focusing on if hydrogen gas is formed, focus on that. So some of these you start a certain place, but this one you jump in anywhere. I would jump in with lead 2 nitrate just because it has the most capitals and the most subscripts, but it doesn't matter. Okay, so I'm going to look at lead 2 nitrate, and there's one lead, lead is good. 2 nitrates, 1 nitrate, I need a 2. As soon as I add my first coefficient, once I add the 2 here for the nitrate, I then look at the partner it's with, potassiums. And then I go to the other side of the arrow. Oh, I need 2 potassiums. Once I put a 2 in front of potassium chloride, I look at the partner for potassium, which is chloride. Go to the other side of the arrow, that's a 2. And then go to its partner, lead 2, go to the other side of the arrow, and there's 1 of each. I go to its partner, nitrate. And once I get back to where I started by putting a coefficient for nitrate, and I ended with the same number of nitrates. Once I've closed the circle, I'm done. If that makes sense, great. And if it doesn't, it will make more sense next week. Or maybe not. I think it will, though. So when I was looking at balancing, I kept chunks of charge, polyatomics all together. I said 2 nitrates on the left, 2 nitrates on the right. But when I do my T table, I need to break it into nitrogen and oxygen. I don't keep the chunk as nitrate.
Sue, where did that I come from?
What I?
That's under next to your K. Your potassium.
My potassium chloride became potassium iodide.
I thought I missed something. Okay.
Oh, you're good. That was me. So the other kind of double displacement or double replacement is acid plus base. Sulfuric acid and lithium hydroxide form salt and water. Ic acids come from 8s. Sulfate is SO4 2 minus. We're going to need 2 hydrogens. Lithium is a +1. Hydroxide is a -1. They come together in a 1-to-1 ratio. Lithium is a +1, but sulfate is a -2, so I need 2 lithiums. And then water, for this and single displacements where hydrogen is formed, I'm going to write as HOH. So this hydroxide, which is made of O and H, is that half of the water. The acidic hydrogens are the other half of water. It's double displacement, so I can jump in anywhere. But I think for balancing acid-base reactions, the best thing to ask yourself first is how many waters can I make? This acid can make 2 waters because it has 2 acidic hydrogens. This base can make 1 water because it has 1 hydroxide. So let me shoot for 2. I want to make 2 waters. Once I do that, the salt always works out. Lithium has, the salt has 2 lithiums. I have 2 lithiums. 1 sulfate, I have 1 sulfate. So when you're balancing double displacements that are neutralizations, focus on this acid and this base. How many waters can they make? And then find the lowest common multiple. In this case, the lowest common multiple was 2. Okay, so nomenclature is super important. The nomenclature, if your nomenclature is not solid, balancing equations is miserable. Even though I'm going to have to test you with the periodic table because of Googling, it's just a reality. I don't want any attractive nuisances eroding your character. When we do these, we're using the actual periodic table. So nomenclature is super important. The next thing I would say is, today we're just looking at these 5 reaction types and how to approach them. So I want to highlight for combination and decomposition, we just start with whatever the chunkier thing is. With double displacement, same thing. Whichever one of these 4 has the most capitals and subscripts, jump in there. For combustion, always start with the fuel and do oxygen last. For single displacement or single replacement, I think I would just look at, what is the messiest. And then anytime we have diatomic elements, those are a good place to reconcile things first. For example, here we had potassium chlorate, and every chunk comes with 3 oxygens, and oxygen gas, which comes in pairs. So a good first place to start would be to shoot for 6. So balancing chemical equations is, first we have to write the formula correctly, so we need to know our nomenclature. And then we're just adding coefficients until we have the same number of each kind of atom on the reactant side and the product side. It's going to be really important that we're comfortable doing this. Whoops, what just happened there? It's going to be really important that we're comfortable doing this. I just lost my thing. Because pretty soon, next week, we're going to take, for the things that are in water, single displacement and double displacement, mostly double displacement. And then we're going to say what's happening in water. And we're going to have 3 equations: the molecular equation, which are the ones we usually look at in the textbook; the total ionic, which looks at how these ionic solutes behave in water. Do they break into ions or do they stay as solids? And then we cancel out what didn't change to come up with a net ionic equation, which is really important in chemistry. And so nomenclature is foundational. Adding coefficients, what we did tonight, that's the easy stuff. And then we're going to use those coefficients to answer more questions in the semester. I do have an extra worksheet that I think I have a key to also. I don't want to assign it, but I'm happy to post it somewhere. And so some of you may feel like, you know what, I would like to go through this step by step with practice and check my answers. And so I will post that for you in keys. And so under keys, it will say balancing chemical equations, and then it'll say balancing chemical equation key. It's not assigned, there's nowhere to upload it, it's not for points, it's simply for learning. If you think that that sounds like something you want, then I will post it tonight for you.